Welcome back, guys. So in today's video, let's see about the applications of Gauss law. So the first one we'll be seeing is due to the infinitely long current carrying conductor. So you'll be doing this video based on what we have learned in the previous one. We have talked about Gauss's theorem, about how to equate the flux to the charge enclosed, and today we'll be seeing how to apply that to different situations. So let's first see the application in current carrying straight conductor. Okay, so first let's see for an infinitely long current carrying conductor. Let's draw the diagram. Let's say this is the conductor, the current is flowing and it's infinitely long, so we'll just consider a segment of length L. The total length of this is L. So we need to find the electric field, let's say at a point P, which is over here. If it was discrete charges, we know how to find electric field. We can just take the sum of individual vectors. But over here, it's a continuous charge flow. That is, let's say all of them are positively charged, because the magnitude is going to be equal. So let's say they all are positively charged. And this is going to emit electric field lines in the radially outward direction. So when you see it in a two-dimensional figure, it is going to look only to the left and right. Okay, so this is how the lines are being emitted, but if you want to see the same figure from the top, then it will look like this. This line, this dot represents the line going inward, and all the electric field lines would be as we have discussed before. But since we are seeing it in two-dimensional, that is from one side, it's going to look like this. We're considering only the opposite sides at a time. So how do we find the electric field lines at this point P? So the first step in any of these problems where we have to apply Gauss theorem is to draw the Gaussian surface. So let me write the steps. Steps for any problem of this kind, any derivation of this type. Draw the Gaussian surface. Suitable Gaussian surface. Gaussian surface. And remember that this surface must have the point you need to find on its boundary. That is, you cannot draw a surface that is only in this region. It must include this point, because this is where we need to find the electric field. So draw the Gaussian surface, and second is use the formula flux total equals Q by epsilon naught, where Q is the charge enclosed. This is the formula for Gauss theorem. But we also know that flux, from the second video, flux is the electric field times the area vector. So electric field times the area, E dot S or Es cos theta. Okay, so this is the equation you must use for any of these formulas. You first find the total flux through the Gaussian surface. After that, you equate it to Q by epsilon naught or Es cos theta, and we'll see how to do this. So these are the basic two steps, that's it. So let's proceed with these steps for this case, and that is for infinitely long current carrying conductor. What kind of Gaussian surface do you think we should draw? It's a line and you need to find the electric field at this point P. So what I'm going to draw is a cylinder. So a cylinder is going to enclose this point P, as well as all the charges residing inside it. So this is the cylinder I have decided to draw, and let's consider this point is at a distance r away from the center. So let's take this to be r. Well, this distance r is basically the entire distance over here. So this is same as this distance, which is r. So the radius of the cylinder is also r. Now let's go ahead with the derivation. So we know the Gaussian surface. All we have to do now is find the total flux. And remember that there are two fluxes over here. One is the flux through the curved surface area of the cylinder, that is this face, and that is phi 1. Let's name it phi 1. And then there is a flux through the upper and lower circular ends, and let's call those two together as phi 2. This and this together is phi 2. So the total flux through the system is, which we need for step number 2. Total flux is phi 1 plus phi 2. And phi is Es cos theta, right? So Es cos theta, this is for the first one, plus Es cos theta 2. Okay, let's first look at the curved surface area. If you take the curved surface area, and you will notice that at any point, if you choose, let's say this point, the area vector, we are trying to determine the angle theta. So the area vector is going to be perpendicular to the surface, as we have discussed previously. So when the area vector is perpendicular, the angle it makes with the electric field lines, which is along the same direction as well, is 0 degrees. So cos 0 is 1. So you get Es in the first case. However, in the second case, if you see any one of these, let's consider this part, the area vector for this circular surface is downward, such that it's perpendicular to the surface. But now look at the angle it makes with the electric field lines. It is 90 degree. So cos 90 is 0. So the electric flux passing through this and this regions are 0. And also, if you think about it logically also, it makes sense. Electric field lines are allowed to cross this surface, whereas in this case, electric field lines are not crossing, it's just going along with the surface. So it's 0 and 0 here, and here you have the presence of an electric flux. Now, Es, but what we need to find this E, so we leave it as E. And what is the surface area through which the first flux is passing? It's the curved surface area, and you know the formula for curved surface area to be 2 pi RH for a cylinder. So it's 2 pi R times the length instead of H, so that's 2 pi RL. So total flux is equal to 2 pi RL. This is the first equation we need. This is the left hand side of the second step. So now we need to just equate this to Q by epsilon naught, and we are almost done. So step number 2 we are doing, because step 1 was to draw the surface. So we have to equate phi total to Q by epsilon naught. So from equation 1, E dot 2 pi RL equals Q by epsilon naught. So we need to find E from here, so you can just directly shift all of these to the denominator of the right hand side. But before that, we need to do one more modification, and that is Q is the amount of charge present inside, but that is for the entire infinite conductor. We do not need that because we haven't considered that. There's so much more infinite left on either sides. So we cannot consider this Q in this Gaussian surface, because a Gaussian surface has a finite amount of charge inside it, and we have specifically drawn the Gaussian surface only for this part. So we need the charge only in this part and not towards infinity. So how do you change this Q in terms of charge that's present only for this length L? Yeah, we have to use the concept of linear charge density. We know that linear charge density lambda equals the total charge residing divided by the length L. So this much charge is present per unit length. So we are going to change the formula for charge in terms of L lambda, so that it's per unit length. And then you'll notice the L from this side and the L from the right hand side gets cancelled off. So let's change Q equals L lambda over here. Yes. So now we have to just rearrange the equation. I'm going to erase the top. Okay, so by rearranging you get E equals 1 by 2 pi RL into lambda L by epsilon naught. So let's lambda and length and length gets cancelled, and you're left with 1 by 2 pi epsilon naught into lambda by r. I'm going to just modify this a little bit so that you know the value of the constant k. So we're going to make this 1 by 4 pi epsilon naught. So I multiplied and divided by 2. So 1 by 4 pi epsilon naught into 2 lambda by r. This is the electric field at any point distance r away from the center of the line. So what's the specialty of this formula is that it does not depend on the length. You see that we have eliminated the length from the formula by using the concept of linear charge density. So now it only depends on the linear charge density, which we know, which is the total charge divided by the total length. So at any segment, if you want to find, this is going to be the same lambda. So in fact, 1 by 4 pi epsilon naught, 2 lambda are constants in this case. The only factor electric field depends upon is r. So that's the thing about the formula. So we have finished for current carrying conductor. Let's go to the second derivation. Okay, so in the next video, we'll see about the electric field due to an infinitely charged plane sheet. And after that, we have 2 more derivations which are very small. So let's see you in the next video.